Great. But anyway, so the question is, when do we stop? Okay. So there is one technique called early stopping, okay, where you say that, hey, I am considering all of these regions, right, all of the split points, okay, but the amount of improvement I get in my error is very small, right, and therefore I stop. I come to some point, so let us say I have like several regions here now, so I consider R1, okay, right, I consider all possible ways where I can pick an x1, all possible ways where I can pick x2 and try to split, and the error does not change by much, okay, I can stop. I do not have to keep going into smaller and smaller regions, even if there are many data points here, I can stop, right. Is that a good idea? So let us go back to XOR. Right. So this is not a classification problem, we are talking about regression. So the x's have an output of +5 and the zeros have an output of -5, right, and you are trying to fit this, right. I can try to look at splitting it on x1. So I have x1, let me speak, I have x1 and there is x2, right. So if I try to split on x1, right, what will I do? Right, I mean the only thing I can do is this, right. So if I split anywhere else, I will be just keeping all the data in one side, right, and all other I mean the other one will be empty, right. This is the only meaningful breaking point, right, and what will be the prediction error here? Whatever, half of it, right. I will be predicting the average of this, right. So let 0 and 5, then I will be predicting 2.5, so it is essentially 2.5 squared into 2, right. What would have been the prediction error if I had kept the entire region as 1? Same thing, right, the average sum square would be the same, right. So if I split on x1, I am not getting any improvement, so let me not split on x1, okay. What about x2? Same, if I split on x2 I will not get any improvement, let me not split on x2, that essentially means that I will just give you the average output for all the 4 data points. But if I split on x1 and then split on x2, okay, now I can do really well, right. So early stopping is usually a bad idea because we will miss out these kinds of interaction effects if we stop too early, right.
But then how do we decide where to split on x1? Anyway we are getting the same thing even if we take the whole data within the
good point, yeah. So in this case, I mean one of them is a trivial split, right. In this case it is easy, but in general yeah, so you will have to take a call, yeah.
What if in case with, like during situations like these you don't split on one of them at one time but both at the same time,
yeah,
and then we see
yeah. So just think about this optimization problem, right. If I am going to split on 2 at the same time, this optimization problem becomes harder, right. Instead of minimizing over j and s, I will have to minimize over j1, j2, s1, s2.
So in which case
it becomes harder and harder.
We could probably carry out a step when we meet some situation like this.
Sure, you could think of other ways of optimizing it, right. So but the most common way of doing it is this. Main reason people do not do 2 variables at a time is the interaction effect, right. I mean, so if you start looking at 2 variables at a time, then I can start thinking of whole bunch of other things. So why do I look at j greater and alone, right. I could think of other combinations, like j1 by xj by xk, right, xj xk, I mean, so then it just starts exploding. So people just said, oh okay fine, we will just do it this way and make sure that we grow a large tree, very large tree, so that we actually capture the interaction effects. In fact, you stop when the leaves are small, right. Think of a tree, right. So the leaf of a tree is a region, right. So the region small, I put it in quotes, it is not the extent of the region, it is the number of data points in the region, right. So small would be like 2 or 3 or 5 or something, or some really small number depending on how large your data set was, you keep growing your tree.
If you say the value.
So if you use some of the standard tools, right, there will be an inbuilt parameter, right, which says how small the leaf should be, right, and you might have to go and twiddle with it. If you are going to use a decision tree function from either Weka or MATLAB or something, right, they have an inbuilt parameter that says how small is the leaf when they stop, right. So for Weka it is 2, right, you might want to change that to 5 or something, I am not sure what is the limit in MATLAB, but you might want to change that. So that is a parameter that you have to fix, right, and it matters, okay, it actually matters, like he pointed out. So if you set it too small, then you might miss things like this, right, and then what you do? You build a very big tree, right, this is what I was telling you, you try to use your greedy algorithm and get the best possible tree that you can, right. So a tree with very small leaves is kind of the best tree that you can build, right. Once you get there, now you are going to ask the question, okay, what is the smaller tree that I can get that performs almost as well as the big tree that I have, right. So there are two ways of doing it. The first one is called reduced error pruning. Okay, it's rather simple. So
When we say leaf size is small, there are many leaves, right?
yeah, each leaf. The largest leaf is smaller than the threshold I set. Okay, so every leaf should be less than that size. So basically, I mean, I can stop each branch independently. So whenever a leaf reaches size 2, I don't split it anymore. So I keep doing, but the other branches can continue growing. So the tree does not have to be of uniform height, right? At some part, some subtree might be shorter, some subtree might be longer, right? So if you remember that picture here, so I kept drawing lines in only one region. So that means that part alone would have been a much deeper subtree, and the others would have been much shallower. So that's fine. So reduced error pruning is something very simple, right. So I have a training set, I build the tree fully on the training set, and then I have a validation set, right. We talked about validation set long time back. I have a validation set. Now what I do is I start greedily, or not greedily, it's very safely pruning away my internal nodes, right. So what I can do, and I erased the only tree I had on board here. Right. So what I do is I have this prediction that I am making, right. I will replace right an internal node with a leaf, right. That's
Joining the regions together.
sorry, exactly. I am just joining the regions together. Now I see the performance of this with respect to the validation set. Right, so I had the original performance on the whole tree, right. Now I look at the performance with respect to the validation set, right. It could go down, right, it could go up, right, depending on how the validation set is, right. I mean, because the tree was constructed only on the training set. When you do the pruning, the error might actually go up, I mean the error might go down, sorry, right, for on the validation set. If the error improves or stays the same, I will keep this, right, but if the error becomes much worse, right, I will put it back.
So does your validation set contain the region?
No.
It is also just
I know the yi's, so I just use the yi's for making a prediction, right, and then I keep doing this in turn.
But this would depend on the validation set then.
Yeah.
Cause more variations.
Yeah. It could cause more variation. Yeah, I agree.
And it's basically joint-
Provided, I mean, usually you use reduced error pruning when you have a large enough validation set, so you can actually trust it, right? And then you try this again, right? And then if it doesn't work, keep going. Yeah.
How did you collapse those two into one node?
So it's like I have this region, right? Instead of that, I just treat this as one region.
But there may be different values on both sides.
No, once I collapse the region, I again do an average on this whole region and use that as the output, right? See, once I collapse, his question is each one of this could have been outputting a different value, right? What will he do with the combined node, right? So I will take all the data points in the combined node, take the average output and use that as the new output for this, right? I could take the average of these two, but why is that not a good idea? Huh? The number of data points could be different, right? So it will not be truly the average of the outputs, right? So if they are having the same number of data points, then I can take the average of these outputs and use it there, otherwise I shouldn't, okay. So I keep doing this. Suppose I was able to prune, right, and now I have pruned this and I have pruned this as well, then I can go back and try to prune that also, right. I can replace this whole thing with this and see how the performance is on the validation set, right.
This is a one-step validation. Meaning, do you do cross validation or?
No, the reduced error pruning is only on one thing. You see, the problem if I do cross validation is I will end up with 5 different trees after the pruning. Now the question is how do I combine those 5 trees, right? Yeah, so,
Thinking that some
huh?
branch might come in one validation and it might go off, like, I mean, it might keep oscillating.
Exactly. So that's right. Reduced error pruning works with only one validation set. It doesn't use cross validation, right? So and for that reason, it is not that popular anymore. Right? I am just introducing reduced error pruning because it's easy way to think about pruning, right? But like as Ishu was pointing out, first of all, the variance will be very high depending on what you pick for the validation set, right? You will end up with a very different tree, right? So just like I mean, already decision trees suffer from very high variance, and reduced error pruning will actually make the variance worse. This is a conceptually easy way of thinking about pruning. And if I introduce a more complex pruning method, right, then little harder, right? Yeah.
How many times can you prune like that?
Sorry.
If you have a large tree, then how many times can you keep on checking?
As long as you are improving.
Isn't that very exhaustive?
Sure.
So, what is cross validation?
I will come to that. I have a whole class planned on all those model selection methods, right? Since he knew about cross validation, he asked me the question, I answered. Yeah, I will come back to that, right? I have a whole lecture planned on model selection. Okay, so cross validation is something guys should never forget once you learn. Okay. The other kind of pruning which we are all familiar with is called cost complexity pruning, right, where you have your error function, right, and you also have your it's there in the name, also have a cost for the complexity, okay, like you had your beta squared in your ridge regression and things like that, right, or norm beta. So you already know about this kind of cost complexity measures, right. So we looked at that in ridge regression, we looked at that in lasso and things like that. And here what we essentially do is we grow the full tree, right, and then what we do is for every possible non-terminal node that you can collapse, right, you collapse that non-terminal node. So which would mean that the entire subtree underneath it you consider as a single region, okay, and replace it with the average prediction for the single region. Like that you can collapse each of the non-terminals and create many different trees, right. So each of this is a subtree of the original tree, right. So what you do is once you created such a collapsed tree, you look at the average prediction error of the tree, right. Essentially look at the prediction error for each data point divided by the number of data points, you get the average prediction error and add a complexity term, right, the prediction error plus some size of the tree, right. So what is the complexity that we are really, so T is a tree and alpha is a parameter, I will come to that. So what is the complexity measure you think is good for a tree? Number of leaves, right, number of leaves, number of regions you have split it into. So that is the measure that we will use. So when I say size of a tree, it is the number of regions that the tree splits the input space into. So alpha is a parameter that controls how small a tree I want. Large alpha means small trees, small alpha means large trees, okay. So now I essentially find my T, okay, which is a subtree of the original tree, right. So it is not any arbitrary tree T, okay. I have a original tree that I have grew that I grew with this procedure, right. With this procedure I grow a tree and then I stop when the leaves are small, and then what I do is I try and collapse each of the internal nodes of the tree. And you can do this in a slightly better fashion, right. You can try to collapse from the lowest level on up and then stop at some point and things like that. But you should remember that it could very well be that maybe collapsing one sub tree alone might not give me much of an improvement, right. But if I collapse everything above it, right, it might give me an improvement. Why? So maybe collapsing this alone does not give me an improvement, but collapsing here might give me an improvement. Why?
Reducing the variance is the average amount.
Because average and left side has more concentration.
Oh, almost there.
You reduce, it keeps it more stable, the balance factor.
Uniform noise.
No, see the point is the error reduction might be small, right, but then I might not have gotten rid of enough nodes, right. If I get rid of this whole thing, right, I get rid of a lot of regions, the complexity of my tree comes down significantly. So even if I am making a slightly higher prediction error, I might be willing to accept that because I have reduced the size by such a significant amount, right. So that is one of the reasons you consider all possible things. Maybe pruning lower down might not simplify the tree enough for you to accept error reduction, but if you go higher up the tree you might actually get the same error reduction, right, error, I mean whatever, by reduction I mean error worsening, right, but you might have reduced the tree by a much larger amount, therefore you are willing to accept that, right. So it is actually not a great idea to just go bottom up, right. So these are small things to remember. Great, so that is something which you pick, okay. Since the magic word has been introduced, so you pick alpha. Who asked the alpha question? Okay, since the magic word has been introduced, you pick alpha by cross validation. I'll tell you about cross validation in a while. Okay, so all of you understand what validation is, right? So cross validation essentially is kind of a multiple rounds of validation, and instead of just using a single validation set, you in fact try to use all parts of your data as validation, right, in a very systematic fashion. Okay, we'll talk about this more detail later, but just to give you a rough idea. And so is this clear? So what we are doing here? Yeah.
You said that if we go the bottom up, we may not hit the right tree. But then how should we go about picking where to start?
No, you look at all possible collapsing, right? So basically what I mean by collapsing, remove an internal node, the entire subtree structure underneath it, whatever regions it was covering, you consider that as a single region and you replace it with that. So I can choose any internal node to collapse.
So collapsing the
Whole subtree and whole subtree underneath it.
Doesn't that mean that it's a very complex thing? You're only showing a small tree. If it's a very large tree, then collapsing each one node and then checking it.
Yeah, it's an expensive process. That's why I said if it is expensive, you can come up with other mechanisms of ordering it, right? But the best way to do it, sorry?
Is there an optimal method to select a node to collapse?
Nope. Nope. Decision trees, there is nothing that's optimal. I mean, right? I mean, everything is hard, right? So, any other questions on cost complexity pruning?
Error could be lowered by including a node at the higher level, so that will also be because of overfitting.
Most likely, yes. But we don't know, right? Until you actually fit it, you wouldn't know. For example, in the XOR case, would you call it overfitting or not? So you wouldn't know, right? Until you fit the data, you don't know whether you are overfitting or not. So you have to grow the whole tree. And if you are overfitting, then when you prune, you will actually end up removing it. I mean, the error will obviously, on the training data, the error will obviously be lower when you overfit, right? And that is why you need the complexity criterion, right? So when I prune, if I don't lose too much in terms of accuracy, then I am happy to prune, right? So any other questions? So essentially what you do with alpha is you pick a good choice of alpha, right, and then try to do the pruning on 5 different validation sets, and then pick another choice of alpha, try it on the same 5 validation sets, you pick another different alpha, try it on the same 5 validation sets, and then pick an alpha that gives you the best
What
thing.
kind of range do you have to expect from now?
It depends on how you are normalizing the prediction error and as well as what is the expected size of the tree you are going to see, right. If the prediction error lies between 0 and 1 and the tree sizes are of order of 10,000s, right, you would really want your alpha range to be small, right. But the tree is also of the order of say 5 or 10 nodes, then the alphas could be larger.